Okay, hi everyone. Welcome to today's live stream. Today we're doing another project presentation. Today we have Sergio with us, who's going to be talking about what's the title?
Compositional paths on hypergraphs.
Compositional paths on hypergraphs. Okay, so I'm very looking forward to this. It was quite an interesting presentation from summer school, and hopefully today we get to explore it in a bit more detail. So Nick and Dugan is also joining us today. And yeah, with that, Sergio, please, yeah, you can proceed.
Okay. Okay, so hello everyone. I will start sharing the screen. Airplane. Okay, do you see the slides?
Yeah, okay,
yeah,
that's good.
Sure. Okay, so in this talk, I will talk about my project on the last Wolfram Summer School that was about paths on hypergraphs, and actually not the classical definition of a path, but a more compositional one, in the sense that you get a path from composing hyperedges in a chain. So this is like a project that involves several different topics. For example, we have a topic called relational algebra, that is a branch of mathematics that was first taught as a theoretical branch, but then it was shown to be the ground of relational databases. So this has many possible applications to, for example, databases or in deep learning, it may also be related. So let me start with the presentation. We're going to see how I use ordered hypergraphs, where the hyperedges are just ordered tuples, and explore the binary rewriting rules that are when you take two hyperedges and compose them to get another hyperedge, and that composition, that transformation, that rewriting rule actually has the same properties as the composition of binary relations. So we are going to study how to extend these compositions of binary relations to high hierarchy relations. Then we will see this from a perspective of quivers. We will talk about these compositional properties that I am mentioning, and we will construct from these paths some algebras. So we will see how to construct some algebras using only hypergraphs, rewriting rules, and this concept of the compositional paths. So let's start by the usual definition of binary relations. This is a very basic definition. Like you have two ordered tuples, and they compose to a third tuple if they are in this way transitive. So xy, yc gets composed to xc. And this is widely used in mathematics. But it is important to review the actual definition of the composition of two relations. That is when you have S and T, that these are two binary relations. What that means is that they are just sets of ordered tuples, of ordered pairs. And if you compose them, you get another set of ordered pairs where this structure happens. That is that xy is in T and yc is in S, implies that xc is in the composition. So that's just the classical definition. And then we can think about a graph, like, for example, this graph, 1, 2, 3, 4, and these three binary edges, the classical definition of graph, as a set of binary relations on a set of vertices. So now we can actually compose binary relations and get paths. For example, here we have a path from 1 to 2, and a path, an edge from 2 to 3, and we compose them to get a path from 1 to 3. So this path will actually be just the ordered pair 1, 3.
So the subscripts, can you go back one? Sorry.
Yes, sure.
So here S and T are binary edges in this formalism.
S and T would be, in this case, would be the same set. That is the set of edges on this graph. Yes, because here we are talking about composing two distinct binary relations, but in the concept of a graph, we only have one binary relation that is the set of edges. So we are composing edges with edges, and so with this definition would be like the set of edges composed with the set of edges.
Okay.
Yep.
Got it.
Okay, so now I want to state this relation between how you deal with sets and relations as sets and matrix multiplication, because I think it can be useful and related to some work that has been done in the Wolfram Institute. So for example, let's say you have three sets, the sets A, B, and C. And the set A is AB, the set B is 0, 1, 2, and the set C is XY. Now you have two relations. The first relation is R between the sets A and B, and the second relation is S between the sets B and C. So it's like it's drawn in the graph. You have these two relations, and then you can actually codify or encode the information of these two relations as matrices. So for example, this matrix means that in the relation R, you have an ordered pair that is A0. Like now the columns will mean the elements on S, and here the horizontal position is going to be the element on R. So here we have an element A0, an element A2, and an element B2, B1, sorry. So this is a way for encoding the information of a relation as in a matrices, as in a matrix. So then you can actually multiply these two matrices, and what you get at the final state, you multiply them. You see here, for example, that you get actually 2, but you are only looking at the information that there exists at least one ordered pair, because we are dealing with sets and not multisets. So we actually get these to 1. And 0 only if there isn't any entry that multiplies to 0, to 1. So what we get is this new matrix that encodes the information of the composition of these two relations. So for example, here we have, when composing these two relations, this is the composition, and the matrix actually tells us this information, like AX and AY is the first line, and the second line is just BY. So it's just for stating this meaningful encoding of the relations.
Shouldn't be like
Yeah, there's
shouldn't be like the other way around. Like you have S after R, right? But you multiply in a different order. So why is it like a relationship property?
Yes. Well, the composition actually, you have like different ways to notate the compositions. Sometimes you notate them to, like, you compose R with S, and you take like the second one first, and then the first one. So it's just there are different notations actually. So some people use it as the composition going from like in the natural order, or in the other way around. This is an example where we take the composition as just the other way around, like taking the second element and composing with.
Yeah, the multiplication on the adjacency matrices is in the correct order. There is one small mistake in that the A in the composition, there are two ways to go. Like A goes to Y.
Mm-hmm. Yes.
There's some. Oh yeah. So A can go to A goes to 0 and 0 goes to Y. Mm-hmm. Also, A goes to 2 and 2 goes to Y. So mm-hmm. in the composition, there are two routes to get from A to Y, and so there's the top right entry in the composition adjacency matrix should be a 2.
Yes, that's right. It should be a 2, but we are only looking at the information that there exists, like one of these pairs, because there will only be the information of A, Y in this set. So you actually will not be able to distinguish between these two paths, like A0Y and A2Y. That's the reason why it's 1 and no 2, because you are encoding just the information of the existence of that pair.
Okay, so I mean, yeah, I mean that information is still captured in the adjacency a multiplication of those adjacency matrices. That you get 1 + 0 + 1 in that top right entry.
Yes.
So, but when you reduce the arity of you don't want double edges. Let's say you simplify the graph.
Yes.
To keep a graph simple, you want the adjacency matrix to have just zeros and ones. Let's say.
Yes.
But yeah, if you wanted to take away that restriction, then you would get a double arrow from A to Y in the composition.
Yes, sure. Yes, of course. If we would be talking about multi-graphs, then we could actually use the 2 and get to 2 different edges. Yeah.
One more comment is like, for me, it seems like arrows should be like another direction, because as soon as you have, for example, you have a relationship from AB to 0, 1, 2, right? It's like from 2 to 3, right? In a way, if you want to represent it as a matrix is usually the output is the number of rows, right? And the input is the number of columns. So your R has 2 rows and 3 columns, but your arrows indicate that it should be like other way around. So yeah, this kind of convention.
Yeah, sure. Yeah, that's true. They would be the other way around, like the direction.
Yeah. Maybe like should be as soon as you transpose it, then it should be also multiplied naturally, because if you want to write the composition S after R, and you transpose the matrices, then you also multiply it in the same order. So I think that's also going to fix it.
Okay, sure. I will change the
are you talking about allowing, like, I mean, because the adjacency matrices are, on the column you have like the A and B, and then on the row you have the 0, 1, and 2, and so you make adjacency matrices to say how A and B items can connect to these other items. And so if you, Nick, are you talking about having arrows go the other way from like 0, 1, and 2 to A and B?
Well, I fixed the arrow if you already draw the picture like that from left to right, but the matrix should be transposed. It's not really the adjacency matrix, because you have a kind of 6 vertices, 5 vertices, then it should be 5 by 5. It's like a bipartite relationship matrix or whatever it is, right? So, but it makes sense for me to just transpose it. Then also the composition would correspond to a natural order of multiplication then, and also outputs would correspond to number of rows and inputs to number of columns. That's also more natural.
Yes, sure. I will fix that actually in the slides. I mean that's not.
I don't think it needs to be fixed. That's just a separate problem.
Yeah, sure.
That's more like a convention, right? It's not really.
It's more like a convention. But actually, like, the idea of this slide is to remember, like, matrix multiplication can be used for encoding the compositions actually. So okay, let's continue. Here we are talking about hypergraphs, where the hyperedges are just order pairs. So for example, the graphics that I compute have some little detail. That is, for example, this hypergraph that is just one hyperedge, 1, 2, 4, corresponds to the idea that we are talking about. Here, this second hypergraph, that is 1, 2, 2, 2, 4, 3, actually has some detail here. That is, if you see the first hyperedge, 1, 2, 2, actually the graphic continues to 1 at the end. So it's like drawing the hyperedge as if it was a cycle. So from the last 2, it goes again to 1. But it is just like the way that it is showing the picture. In fact, when you code it, it is actually 1, 2, 2, just that information, and the other one is 2, 4, 3. So that is just a comment on how to interpret the graphs here. The
visualization of it. Yeah.
Sure. So okay, these are another examples of the hypergraphs that we are going to be talking about.
Yeah, okay. So the different colors there, just so that people understand, because many of our audience are still learning about hypergraphs, right? So the blue on the top, the 3 loops, is showing the 1, 1, 1 edge. And then there's a separate edge in the orange, which is 1, 1, a self loop, and then a 1, 2. Is that how this works? Okay. And then the bottom one is like a 4. Is that a 4 edge? How would you describe a 4 arrows? Is that the right way to describe it?
Yes.
Between 2 nodes of 1, 3.
Mm-hmm.
And that's 1 edge.
Yes. This is just 1 edge, exactly. And hypergraphs are like important because they are just a generalization of graphs. In graphs, you only have order pairs, but here you have higher arity relations that are occurring within the set of vertices. So that can be more powerful to encode, for example, relations in data or things like that.
Got it. Thank you.
Okay. Okay, now we'll talk about this little concept that is what is a quiver. That some of you may know this as a multi-directed graph. So quivers and multi-directed graphs have the same structure, but quiver is the word for when you are talking of them, like from the algebraic point of view. So what I mean with this algebraic point of view is that you will take these sets Q0 and Q1, that they are actually the set of vertices and the set of edges. The set of vertices will be just some points or sets, depending on what you are modeling. And the set of edges will be some functions or morphisms. In for example, in category theory, they use quivers to represent how a category works. And you have these 2 functions that are S and T. And these 2 functions, what tell you is actually the information of where an edge starts and where an edge finishes. So S is the source of an edge and T is the target of an edge. So these are functions from the set of edges to the set of vertices. So for example, here we have the source of F6, that is this function, is X, and the target of F6 is C. So that is just the usual classical definition of quivers. And we actually are going to talk about quivers because we will take quivers and construct something that is called the path algebra. This is for taking the way in the paths, like the way how the paths in the graph are arranged to construct an algebraic structure. So let me show you how this can be done. If we have a quiver Q, and we choose any field K, just any field that you want. For the ones that don't know like fields, it can be, for example, real numbers. Yes. So you choose a field and a quiver, a multi-directed graph. In this case, we have here 1 point and just a cycle going from it to itself. And you define this operation that is going to be just the multiplication of paths, that is just the concatenation. Yes. So for example, here the path is named alpha. So if you take alpha and travel twice in alpha, you get alpha alpha. That is just is going to be like a word that encodes a path, like concatenation. And then you define these identity elements that are the E sub I, that there is an identity isubai for each vertex. So for example, here we would only have E1, and it is just for constructing the identity of the formal algebra. Yes. So if we have a path that goes into 1 and is composed with E1, it will be the same path after composing. And if it is not the target of the path, of the edge or of the path is not I, then it would be 0. Yes, this is for creating the actual identity element that is going to be the formal sum of these identities in each vertex. So the formal sum is just the linear combination of all these E sub i's in all the vertices. And with this concept, you then can take the path algebra, that is just taking the edges and taking the concatenation of edges as the paths. And with the paths, you define all the formal sums, like all the formal sums of the paths. And those are going to be the elements on the path algebra.
Is it necessary that every element in this quiver, that every vertex needs a self loop for the
no,
the
this
identity
is just
elements to exist?
This is just an example, but actually the identity elements are not self loops, but are just they cannot be visualized in the graph. They are like doing nothing, like getting to a vertex and doing nothing. But you need that notion for defining the sum of all the elements that do nothing to be the identity on the algebra. Yes. So for example, in this example, we have one vertex here, 1, and the one edge that is alpha. But this is not E sub I, but the edge that goes from 1 to 1. But the E sub I would be traveling this and doing nothing, for example, would be the same as just doing alpha. The E sub I is like a not visual element on the graph.
Okay.
Yes. And then you take those E sub i's, sum them around. And what this line means is that you get any element on the path algebra that is just a sum of the elements on the field and the paths, like any linear combination of the paths. And if you multiply it by this identity that we constructed, that is all the E sub i's, they actually are identified with themselves. So this element on the path algebra goes to itself after multiplying with the identity. This happens because we are taking like a linear combination of some paths on the graph. And then for each of those paths, you will be actually composing that path with the vertex, with the E sub I corresponding to the vertex where it finishes. So they are just taking like these E sub i's and composing them with every element on the linear combination here. And then if you do that, the only one that will live, like that will last, will be the one that the E sub I corresponds with the vertex where C finishes. So it's just like doing nothing to the initial element. But this is the notion of the identity on this path algebra. And with this, actually, we construct these formal elements that are not paths on the graph by themselves, but linear combinations of paths.
There you go. The question. You have this identity element property that your target, if C is your path, right?
Mm-hmm. Yes.
Then you can get rid of the identity when the target of that path is the node of the identity where this identity lives in, right? Mm-hmm. But in the sum, when you remove all of those identities given a single C, how can the target be like of the single C path everywhere? Because those are like different kind of vertices.
Yes, But here, for example, when you take here the combinations of paths, in each element of this sum over the paths, you actually multiply that specific path with all the isobites, So the only one that goes for itself and not zero is going to be the one that is with the corresponding isobite. So the only one that lasts.
Okay, you're summing over them. So
yes.
So then when you bring it over to the sum, essentially you already remove a bunch of them, right?
Yes.
Okay.
Like almost all of them will disappear, except for the one that is the corresponding isobite.
So your first equality is essentially you already removed all the zeros, and then the second equality is when you use the identity, the first one in the piecewise function. Yeah. Okay.
Yes. So that's how like the path algebra works. So an example for this graph that is just one vertex and a cycle is that all the paths will be concatenations of alpha. So they will be like alpha squared, alpha cubed, alpha to the fourth. But this, you have to take into account that this power is actually just a word. You are taking words, concatenations. And when you do this, they act actually like if you had x squared, x cubed, because you take all the possible combinations within the field K and these generators. So you can say that they are actually isomorphic to the polynomials in one variable, because you can have 2 alpha plus 3 alpha squared, something like that, and any polynomial that you want, depending on the field that you choose.
Okay.
Yeah. So that's the idea for constructing the path algebras, and this is like the classical way for constructing path algebras. So now
I'm sorry. The identity elements are a way to select. It looks like certain paths. So if you want to like say, okay, well, I have all these paths, and I want to select the ones that end at a certain vertex, then you can multiply all these paths by that selector element, and it'll return. It'll be like multiplying by 1 for the paths that end there, and then multiplying by 0 for the paths that don't.
Yes, they can be used like for selecting, but this identity is isobise. But the actual use is to construct this sum, that is the sum of all isobise, because we want to construct an algebra of linear combinations of paths, not just an algebra of paths, but linear combinations. And the way for actually getting an identity on the linear combinations of paths is getting the sum of all these isobise. So each of these isobise is not actually an identity for the paths, but for some specific paths. But those are not like the actual identities of the algebra, but this sum of all the isobise. Yes. But again, like this is only for taking like a graph, a quiver, taking its paths and generating some formal algebra, like the linear combinations of paths, and see how that behaves. Like that's the idea. Okay, so now that we are like in the context, we can actually start talking about the ideas of the project. That the initial idea was to construct a path algebra on hypergraphs, taking paths as compositional paths that are just any chain of composition of hyperedges. So for doing this, we actually need to study some things. For example, we need to define how to compose two hyperedges, because they are not anymore binary relations, but high-hierarchy relations. And there is no a consensus in the mathematical framework on how to compose two NMRT relations. So this was just the beginning. So we have to make the distinction between the concatenation paths and the compositional paths. Concatenation is actually notated like just one vertex and all the concatenated edges that you traverse and the last vertex. Here goes a comma as well. So you get just a sequence of vertices, a word of vertices, going from one vertex to another one. But when you concatenate, when you compose relations, you are actually doing this function that we are going to study how to generalize this function to the set of hypergraphs and not only for graphs, because there's something important here. That is that the compositional paths on graphs are not really like interesting because they only encode the information about the starting vertex and the last vertex. So they are leaving out all this medium information. But when you get this composition of binary relations, take its properties and define these compositions for high-hierarchy relations, they actually are able to encode more informations of the middle steps than in graphs. So this is like the starting point, that in the compositions on graphs are not really interesting because they just encode this information about the initial vertex and the last one. But when you compose high-hierarchy relations, you actually can get information from the middle steps. So let's see how to actually get that. We need to define
one.
Yes, sure.
So I guess the composition of alpha, beta, and gamma here will make a composed path from 1 to 4.
Mm-hmm.
But the object 1 bar alpha, beta, gamma bar 3
mm-hmm.
is a path from 1 to 3. Do you mean 1 to 4? There or in that first?
Yes. That's 1 to 4. Sure. Yes.
Okay.
Yeah.
And this is 1 to n. Yeah. That's typo. Sorry for that.
Okay. Yeah. On the previous slide, there was a similar notation, so you might want to just check that.
Okay.
There as well. Okay. So it's a 1 to 4 edge after the composition. Is that correct?
Yes. Here is 1 to 4 in the alphabet diagram. Yes. Sure.
Okay.
And here it's n, I think. And here also, but yes, that's like the way for writing the parts. Okay. So I was saying that we now need to take this composition of binary relations and generalize it in a way that we get a class of rewriting rules that in the binary case, they are only like the binary composition, but in the high-hierarchy cases, they can be more interesting. So, well, by binary rewriting rules, I mean just taking 2 hyperedges and rewriting them as another hyperedge. So we are actually going to study a class of these specific rewriting rules. So, for example, the properties that we need in order to generalize the compositions of binary relations can be these ones. They can be a little bit different. For example, they can be more weak to allow more rewriting rules. In the community post, I made some notes on which one of these properties can be weakened and you get more rewriting rules. But the ones that I chose for studying this class of rewriting rules were the ones that are endpoint preserving, meaning that if you compose two hyperedges, then the composition must start on the initial vertex of the initial hyperedge and the last vertex of the last hyperedge. The direction compatible property is that the rewriting rules need to compose hyperedges in a way that the last vertex of the initial hyperedge is attached to the initial vertex on the second hyperedge. This can be weakened. This is the one that I was talking about. You could also compose 2 hyperedges where the initial vertex on the second hyperedge is not the last one, but some middle vertex. And the other property, like the next property, is external vertex selecting. That is just that you are not going to add more vertices, but you are just going to get subsets of the initial vertices that are external. In this case, the external vertices are 1, 2, 4, 5, and 3 is the only internal vertex. But you could get some subsets of the external vertices. And this actually is a little different than saying that the middle vertex is deleted, that 3 is not going to appear in the composition. But you can actually study those two properties, that middle vertex selecting and external vertex selecting, in a similar way. So I'm just focusing on the middle vertex deleting. And that's it. Connected rewriting rules only is for saying that you compose two hyperedges and you cannot get two non-connected components, because that wouldn't be one single edge. So that is the connect.
That also like should be a single hyperedge on the right hand side, right? Because that's the rule. Not just it's disconnected, but it's like actually two edges.
Mm-hmm. Yes.
By definition, that single edge can be really disconnected.
Mm-hmm. Yes, actually, you get that property from the definition of binary rewriting rules. Yes. And so now we have these properties that are the properties that you get from compositions of binary relations. And we are trying to generalize them to compositions of hierarchy relations. So here we have some examples.
Question on the previous slide. Are N and M and L fixed here, or is it to say that you take an arity edge of an N arity edge and try to compose it with an M arity edge, and you'll get an arity edge of some it's not necessarily known given the inputs.
The N and L are not fixed. You could have all the binary rewriting rules for different combinations of them. Yes, that's.
And so can you go through the one on the left? So you have I guess it's ordered. You have a 1, 2. No, I mean the diagram here on the slide on the left. Okay. So you have the blue one is the edge 1, 2, 3, and it's ordered like that, I guess. And then the 3, 4, 5 is ordered. And you take out the middle, the one that's in common, right?
Yes.
And then you have two separate edges.
Yes, this is for showing that this cannot actually happen. Like this would violate the connected writing rule, or just the definition of getting one edge. Like this is not actually an example, but for saying that you cannot have this scenario where you get two different edges or a disconnected components. The one on the right is the actual example.
Yeah, it's answering the question
of the
allowed.
So this is trying to take a composition of two hyperedges.
Yeah,
exactly. And the one on the left is not the composition, but the one on the right is.
Exactly. Yeah.
Okay.
Yeah, it's answering the question there. Which ones are the compositional properties? So the one on the right is, and the one on the left is not. Yeah, got it.
Yes.
And essentially all you're gonna enumerate here is just all different hyperedges that are like constructed on top of those external vertices. Because if your property is delete internal one, and you also only allowed to have a single hyperedge, so essentially you just enumerate all different orderings or symmetries of the giant hyperedge constructed on top of external vertices, right?
Exactly. Exactly. So, for example, here we have two ternary hyperedges, and these are all the possible compositions with these properties. Like there are only four possible compositions of these two ternary hyperedges. So you here have 1, 2, 3, 3, 4, 5, and you compose it to 1, 5. This is the notation that I will explain in the next slide. But this means like you are composing a ternary hyperedge with a ternary hyperedge. And these parentheses here means that you are not getting elements from the middle. So in these parentheses, you could actually have some subsequence of the vertices. So this is empty subsequence, and 3, 3 just means that you take just the initial vertex and the last vertex, 1, 5. Here you have 3, 3 and the second element on the first.
How do we define which one is the last one? Because only the single vertex number 3 is the common one, right? The fact that you have an arrow, that's essentially already incorporated direction.
Yes, but you define the last one because in the way you are defining like the binary compositions, the second hyperedge that you are composing is going to tell you the last one. And that is because if you composed, if you use this composition in a non-direction compatible way, then it would yield an empty set, like composing two edges with where the direction doesn't match in the middle vertex would
so these are empty. Directed hyperedges. Basically, the 1, 2, 3 is a tuple, not a set.
Yeah.
Specifically, you're not allowed to rearrange them; they go in an ordered way.
Okay.
And it's structured.
Exactly.
Okay.
I have a question with your notation there. So you said it's the last vertex to the last vertex of the second hypergraph. But isn't one the first vertex of the first hypergraph? So if it's 1 to 5, shouldn't it be 1, 3 in your notation?
No, because you one of the properties is that you always get the 1 and the 5, like the endpoints preserving. And what these subsequences tell you is the middle vertices that you are getting. So for example, you get the second vertex on the initial hyperedge and it's 2. And in this one, you get the second vertex on the initial hyperedge and the second one on the second hyperedge, and you get 1, 2, 4, 5. And you always delete the middle vertex.
Yeah, I'm just thinking in terms of if you had like let's call them nodes. If the nodes were labeled, then 1 would be would 1 be the first node of the first hypergraph, 2 would be the second node, and 3 would be the third node. And that also corresponds to first, second, last. So if you're going in the result from 1 to 5, if 1 is the same vertex as the first vertex in the first hypergraph, then shouldn't that be first to wouldn't that be 1 of the first hypergraph to 3 of the second hypergraph? Nick, I don't know if I'm making sense or Dugan, if you follow that.
Let me see.
I'm not able to annotate this screen share. I think this was using Linux. But yeah, if you put your mouse over the first version there, so but to the right, you can see there's a 3, 3 in your annotation.
Yes. So that 3, 3 is only for saying that you are composing ternary hyperedge and ternary. No, it doesn't mean anything about the vertices that you choose, just that you are composing a ternary with a ternary.
Got it. Okay, I thought you were saying that that's the number of which vertex remains. But okay,
yeah, no, it's actually just.
So it's in the definition. What you're saying is you've predefined that it's the first and last.
Yes.
Okay.
I have it like, for example, you take a set of vertices, 2 NRE relations that are just sets of tuples, and 2 fixed subsequences of the middle vertices. Yes, without taking the last one and nor the initial one, because you will have actually the initial one and the middle vertex between the 2 hyperedges will be deleted, and you define the composition like this. Like you have two sets of ordered tuples of different arities, and you compose the tuple S1 to Sn and the tuple T1 to Tm as taking the initial element, taking a subsequence of the middle vertices that doesn't finish on the middle vertex, and then taking another subsequences of the middle elements on the second hyperedge and the last vertex. And if there is not this condition that Sn, like the last vertex on the first hyperedge, is the same as the initial vertex on the second hyperedge, then the composition would yield the empty set.
Okay, that makes
So,
sense. So
yes.
just add this so the full screen concept. Okay, do you mind just going back to the previous slides so we can understand each of those scenarios?
Go back to slides.
This one.
This one.
Okay. So all of these compositions, there's four. Is it right to say there's four compositions here, and each of these are valid compositions?
Yes, all of these four are valid compositions between, and they are all the valid compositions between ternary and ternary hyperedges. Yes, there are only four. And actually, you can count how many of these compositions are there for a given n choosing. So if you get n and m, you are just getting this information, like this subsequence and this subsequence. So the subsequence is just any way for taking the middle elements, and that is actually 2 to the number of elements that you take. So this would be just n squared plus m squared minus 2, because you have the first one and the last one.
Okay, so
yes, not just n squared plus m squared.
In this case, you can
minus 2 in the exponent.
You can take all the s's s sub I, I guess, all the way up to s sub n minus 1. There are restrictions, right? So you can take, like, if like these four and these four like match up on their common, this one's the last one and this one's first one. You can take those out, and then like you can take up to 3 of each, as long as you keep the first one and the last one, I guess.
Yes.
Okay.
Yes.
Another thing, is it allowed to actually permute S's and T's? Right?
No, you cannot permute them. Like you are only like taking subsequences and gluing them. Like it's the idea.
Well, what about just S's? If there are multiple S's that we preserve, can we permute them?
No, you cannot. You only get like the order is fixed, and you get the subsequence in the same order. That is for.
No, but is there an argument for why you have to like pick?
Yes, because, well, I was like seeing at this property that was taking the direction on the initial hyperedge as some sort of relation on the data of the vertices. So it was like for preserving the direction on the initial hyperedges to the composition of them. Like, for example, in a database, for example, if the relation means just you can access 2 going from 1, then you would not desire to take the compositions that change that, because then you could not do that. But it was just for taking the same order that you had in the initial hyperedge.
Yeah. Well, not yet very obvious. Like on the previous slide, you could have had like 1, 4, 2, 5.
Yes.
Right. So that they like crisscross each other. Not necessarily obvious why we can't compose like that.
Yes, this is not like obvious, like that you could compose like that. But well, it was just a way for taking deleting some information from the initial hyperedge. But
I'm talking about the largest one. That's like the one that goes vertical, straight down. Yeah, when you have the largest hyperedge on the right hand side, 1, 2, 4, 5. Because in theory, you can. Like, it's not obvious to me why it's not allowed to swap 4 and 2 vertices in this hyperedge, just so that it goes from 1 to 4 to 2 to 5.
That actually could happen if you had the initial hyperedges where the vertices were the same. So for example, if you had, instead of 1, 2, 3, 3, 4, 5, if you had, for example, 1, 2, 3, 3, 2, 5, like if they are attached in that way, then you would see a behavior like they are getting switched, but it's not really that they get switched. You just have
because
like
the same. When they're actually the same, it's not really switching anything.
Exactly.
Yeah, but yeah, okay.
Yeah.
Maybe you have some other examples when it's obvious, when you some properties that forbid this kind of behavior. I don't know.
Okay. Let me see. Well, it was just like the idea was just to preserve the directionality of the initial hyperedges. That was the idea that we were thinking when.
Yeah, it's just in the graph case, you just drop all the intermediate vertices anyway. If the only motivation was to keep some information in the intermediate vertices, it's like it doesn't matter what actual information and how we preserve it. So that's why my intuition was you can do whatever you want in those in intermediate vertices. You can permute them in any possible way.
Okay, yeah, sure. You could generalize the composition with also allowing permutations, but then you would not be taking the information of the directionality on the hyperedges. That could be also defined, but it could be also defined for non-ordered hyperedges.
Well, you still preserve it because you still have the source and the target of the whole hypergraph with those two hyperedges the same, right? 1 and 5 are still the start of the target. So if you compose it with other things like that, you don't care what happens in the middle. It's just you're just taking some more convoluted path in between.
I would say that given that this is looking at a lot of possibilities of how to, I mean, there's like the canonical thing to do would be to take this tuple and this tuple, and if they agree on the middle terms, then you could take that term out and construct the resulting tuple. Basically, just go from 1, 2, 3, 3, 4, 5 to 1, 2, 4, 5. And then the rest of these are just sort of dropping some of the intermediary terms at will from this. So the so if since these things are ordered, then you can kind of look at it like you drew it, like okay, the 1, 2, 3 arity hyperedge can be thought of as a graph with binary edges between subsequent terms. So you have the 1 to 2 and then the 2 to 3. And it's just sort of you're joining these two graphs. These two sequences of edges. And
there's
so in that sense, like on the concatenation of the two graphs here, then you can have a composition between the arrow, the 2, 3, and the 3, 4 arrows, and connect that with the 2 to 4 arrow, and then you get the graph on the bottom left. And that whole graph is a sequence of edges is treated as an arity 4 hyperedge.
Yes. Yeah, there's a comment here that this drawing means that this is just a ternary edge. Like you are not getting the binary edges here. It's just for saying that there's a tuple here. But
right, that is ordered. There's an ordering to the 1, 2, and 3.
Yes. Yeah. Yes. Okay.
Yeah, so it's a separate discussion thinking about the hyperedges as sets that can be permuted in any order if they're just like bags of points or multi-sets where some of the items can be repeated and you have like self arrows.
Yeah.
All right.
Well, yes, it's true. In fact, if we were talking only about hypergraphs as sets of vertices, with this being not a tuple, an ordered tuple, but just a tuple of vertices, like the most natural way to define like the composition would be just having all the possible permutations here that Nick was mentioning. Like you could define that in that way. But if you do that, you actually lose the information of the direction between the hyperedge.
And you're saying that's very important with regards to how we do the composition.
Mm-hmm.
Got it.
Okay. Okay, so these operators, actually you can only compose tuples that are of length n and of length m. These are designed only for these tuples. These n, m are fixed. These ik, yk bar are just variable. You can get subsequences, but n, m are fixed. Like each n, m will define one composition. These ik, yk are just notations for these subsequences here. And then you would want to have operators that can act on variable lengths of tuples. So for example, you would want to have an operator that can compose an mn or kl, but acts in some subset of the vertices, the middle vertices. So let me show you how that would be defined. Like here is the definition, but let me show you like the example first, and then we return. That is here. We define these operators that take the composition 3 parentheses empty and perform it in the last 3 vertices and the first 3 vertices of the tuples. So you get a way for defining these operators so that you can apply them to larger or narrow or well only larger tuples. Yes, like variable tuples. So here we would have actually functions where the xn and xm are not fixed, but there's only this x that is the set of all tuples of finite lengths in any length. And we get this definition of the composition of the composition operator of those tuples as being taking the first alpha minus n elements, like then this is the Cartesian product, but taking the elements out. I will show you how. Let me here. For example, here we are just getting one tuple at the end. So this is just one going to be one tuple. Of course, the usual Cartesian product would get a tuple, comma, another tuple, comma, another tuple. But in the context of relational algebra, that is one theory that has studied similar topics. You define this operation as just like concatenation. So you get the operator for composing any length of tuples in the way that the initial operator was acting. That's the purpose of this like triangle operator. And well, the purpose is actually to get this triangle operator to define an algebra on the hypergraph. So you can see here like how it works. You take the first vertices and concatenate them with the composition of these middle vertices that are n, m, and they get composed as the other operator, like the circle operator. And then you concatenate with the x9. I'm not sure if that's like clear.
So here the 2 hyperedges are joined on the 5, and you're taking out 4, 5, and 6.
Yes. And
as a joint.
Yes, but I am taking it by applying this operator that performs the circle operation between these 2 subsets, like between these 2.
Did you say sequential operation? What? What operation?
This is, well, I named this the compositional operator, and these are just the compositions and the compositional operators.
Go back to that picture, sorry. Yeah,
Yes.
So the subscripts of 3 indicate that you're trying to get arity 3 out as output, or I thought those were as input.
Yes, these subsets of 3 indicates that you are going to perform this composition between 3, and you get those 3 elements from any tuple just by getting the last 3 and the last 3 here.
I guess it's a little confusing. I thought, so what are the superscripts indicating?
The superscripts is the same, like taking the subsequence, empty subsequence, and empty subsequence. So when you perform between these 3, 4, 5, 5, 6, 7, the empty subsequence and empty subsequence, you only get 3, 7. So we are doing that operation, but between the larger tuples. That is the purpose. For actually being able to apply it repeatedly in a chain.
Yeah, I'm also kind of like trying to figure this out. So on the right hand side, you've got maybe if we just break it down. So on the right hand side at the top, we have a quadrilateral, or how would you say that? A 4, 1, 2, 3, 4, like a 4 hyperedge on the left, and then a 4 hyperedge on the right, connected with the vertex ID 5, right? So, and then if you look on the left with regards to your notation there, the 5 is the same vertex in both of those edges. So if you take your notation with the 3, 3 below the triangle, the first 3, does that point into, is that always the last 3 nodes of the hyperedge on the left?
Yes,
and then and then the second 3 is the first 3 nodes of the hyperedge on the right. And then what are you doing with those? Are you
like you take that information and you compose them with the circle composition, like they were.
Oh, I missed that. Okay, so there's a triangle and then there's a circle. Different type of composition. Okay, thank you. Okay.
What's a triangle mean then?
Yes, the triangle is for applying the circle composition, like in when you actually don't know if the tuples are of length 3, 3, but any length and any length higher than 3, and you want to apply this circle composition in the middle vertices, like the circle composition.
Okay, so maybe it would be nice to have nice names for the different types of compositions. So the triangle composition, what have you named that?
The triangle, I named it the operator and the operators, and this one's just the compositions. But here the title is just for compositional operators. These are NM compositions. Yes.
Okay. Maybe we can find a more nifty name for them, like the triangulator, or the circular something. Carlos is very good at coming up with names for mathematical things. So. Okay, very good.
Yes.
Okay, now we got it.
Yeah, sure. Okay, so this this seems strange, but the purpose of defining this triangle operation is to actually letting higher arity tuples that when you don't know the arity be composed in a fixed way that you want. Why would we do that? Because we are going to define like an algebra in the hypergraph. So let me show you how that can be done. This is an example of a classical path algebra on this hypergraph that is just alpha, beta, gamma, and a compositional path algebra. Like this is using these compositions. Like here are just the binary compositions, just the usual ones for getting the sense of it. So you have here the adjacency matrix, and you get from this graph the algebra of triangular matrices. That is because, for example, from 1 to 3 you can go alpha beta, but from 3 to 1 you cannot go in any paths. Like, so all of these ones are going to be 0. Here you have the identities that are for each vertex, and then you have these ones. Yes. Okay, so we can talk of them as words of the edges, but we can also talk of them as ordered pairs of vertices. So here we have the ordered pairs and the compositions to like the compositions that they resemble. So alpha beta is just composing 1 2 with 2 3 and goes to 1 3. So in fact, you get like the same path algebra using concatenation and composition in this example. In general, they are different. Let me show you one example where they are different. But here we are just seeing how to construct the same object like this, the path algebra, but we instead of the concatenation operation with composition. Is this slide clear?
Yep.
Okay. So this is an example where you don't get the same path algebra. So you have this graph, just one vertex and the alpha, and we saw that it's the polynomials algebra. But if you do it with composition, you just have like 1 1, and when you compose 1 1 with itself, it's also 1 1. So all the elements are the same. You are not getting like this chain of different elements that are words, increasing words, but you get always the same ordered pair. So you just get K. So it's not doing realizing the same algebra. So one could think how to construct the algebra of polynomials with these compositions. How could we construct the algebra of polynomials with these compositions? So, well, here this is just for stating that we are in the composition, we are taking the operation of the algebra to be these triangle operators. So let me show you a way for doing this, like for taking the polynomials with the compositions. So let's say you start with this hypergraph that is just this hyperedge 1 1 1, and then well, if you graph it, it will be actually three leaves because it's matching the last with the first one. But you can see it's better like here 1 1 and 1, and you perform the composition triangle 3 3 2 2. And that means that you are taking the last 3, the first 3, and taking the second element and second element of this. So you get actually then the first element, the second element for the subsequence, the second element, and the last vertex. So you get actually a 1 1 1 1. And if you perform it again, you will see what was the purpose of these triangles. Because if you perform this triangle again, you will compose a fourth arity with a three arity hyperedge. And we could not apply the circle operation between these two. So we would have problems for creating this ascending chain with the circle operator. But with these triangle operators, you can actually get ascending chains of arities. So when you compose this 4 arity with this 3 arity, you get the initial one. Let me see. I missed one here. Let me see. 1 2 3 4 5. Yes, this should be 5 ones here. Like in every operation, you add actually 1 1. Yes, sorry for this. but that's like how you get an ascending chain of different elements that are actually the elements on the algebra from this compositional operator. I'm not sure if that's clear here, because here should be 5 ones and here 6. Yes.
Take a moment to see if we can understand this.
Okay.
So is the intention here to say what would happen if you multiplied an edge 1, 1, 1 by itself 3 times? Like we want the polynomial representation of hyperedge.
Yes, like the intention is to construct this same algebra of polynomials that we constructed in the classical sense with this graph and concatenation, but using compositions, because here we didn't get the same. So we take this composition and we see that if we start like composing this one with itself and again, we get an ascending chain of different hyperedges. That's the idea.
So the way to get polynomials is by specifically having your operator there with the 2, 2 in the brackets at the top. Okay.
Exactly. Exactly. This is an example of how you could get polynomials with compositionals, with these compositional triangles and this starting hypergraph.
So it's a type of compositional. So maybe one way to describe it is that with this compositional operator that you've defined here, you actually get different types of algebraic properties depending on which compositional you decide to utilize. That's pretty cool. That's really cool.
That's the idea. So the idea is that as you have many different choices of the operators, you can actually have, for example, a class of operators that are associative, or you could have a class of operators that are not associative, or different ways in which they behave.
Okay, and this one is specifically, so the 2, 2 at the top is concatenation.
No, it's supposed to be compositional.
Composition. Okay.
But it's limiting how much it takes away from the middle part.
Like these
so
two are
it
just
gets longer each time.
Like it's applying this composition. Let me show you here. This one, like the fourth composition here, where you compose 2 ternary and got a fourth arity. It's applying that circle 3, 3, 2, 2, but you need to define the triangle because you are going to apply it to higher arity or higher length tuples. Yes, for example, here you apply it to 4 and 3, and here you would get 5 instead of 5. Yeah.
Cool.
So that's how you would do it. So okay, so what we did was to define actually some operators for hypergraphs that are rewriting rules, but can also be talked as operators for relations. And there is this branch that is called relational algebra, where Edgar Cote established like the base of the database industry. So this relational algebra theory is actually what they use for studying how SQL or relational database languages work. And the purpose is to define some operators that transform input relations to output relations. And that's what we did. And you can do those operators, you can define those operators in different ways, but we defined a certain type of operators that can actually help us construct these path algebras, for example, on the hypergraphs. And then there's the question if all path algebras that you can construct in graphs are or also can be constructed in hypergraphs, because surely you can construct compositional path algebras in hypergraphs that cannot be constructed in graphs in the classical sense. But the further research question that I will talk here. Let me also make a note here. This Cartesian product is the one that we are using, the cross join or cross product, like just concatenate. And well, then there are some related works. I'll tell you about them, but first let me show you this. Like the further research idea is to see if all possible path algebras can be encoded in this with these compositional operators as compositional path algebras. That is one of the main ideas. Is it clear, like the purpose of defining these operators?
Yeah, makes total sense.
If you have like an actual example from relational databases, that would help. Like how those
okay, no,
operations compile to this kind of product.
Okay. Well, for relational databases, like this is just a theory that we found after creating some of these process that was related with what we were doing, but we have not actually talked of it as in relational databases for creating it. They were just for creating a way of constructing algebras on hypergraphs. Like that was the motivation. And then we found that that what we were doing was actually related with this relational algebra branch. That was like the process.
That's very cool. So is there some direct connection to languages like SQL?
Yes. Well, with the things that we did, we haven't like searched for the connection with SQL and that. But this relational algebra is actually was actually used for creating relational database languages. It's like the theoretical background for all of that.
That's so cool. Yeah, I always had a feeling there was some kind of important connection between the relationships in hypergraphs and SQL. Like the way relational databases are structured, there's some kind of important connection there.
Mm-hmm.
That's
yes.
very cool.
There's also one comment here that is that what I have encountered in relational algebra is that you always work with fixed length tuples, like just the same arity, but higher arity, but the same arity in all your computations. But we are seeing some mixed arities operations here. That's something different, like a little bit different, to what is usually done in relational algebra.
Makes sense.
Yes. And then there are also other related works. For example, this was actually a motivation for some of the definitions that these three people here studied compositions of ternary relations that are just like 6 basic compositions of ternary relations. And well, they studied them from a more set theoretic point of view, but it was like a related work for hierarchy compositions that I wanted to mention. And there's also this work that is the only one that I have encountered where they construct path algebras on hypergraphs. And in fact, it is different because the operation that they use is it resembles more concatenation like than a composition. But they are actually very good. Like this paper is really cool because they use these path algebras, like the Leavitt path algebras, that is a classical concept on representation theory. And they construct a generalization for hypergraphs of those. So this was worth mentioning because it's the only one that I have seen where they work with path algebras and hypergraphs. And this is like the last related work. That is that Greg Young. He was at Microsoft Research, but now he's at XAI. He's the one that developed the theoretical framework for some deep learning techniques, for example, hyperparameter transfer learning. And he developed what the concept of a tensor program where you have just a composition of matrix multiplication and coordinate-wise nonlinearities. So I wanted to mention this because of the first slides, where I mentioned that relations, binary compositions of relations, can be talked as multiplications of matrices. Maybe we could see then if compositions of high hierarchy relations can be talked of different ways to multiplicate hypermatrices, like in the way that Carlos and in the institute you are studying. Like this could be also related.
Very cool.
And that was like the further research. So compositions may viewed as products of hypermatrices. Study if these compositional operators encode the classical path algebras, like all of these classical path algebras, because we have constructed some analogs, but it would be cool to have a theorem to state that any path algebra on a graph can be transformed to taking this hypergraph and this compositional path algebra on this hypergraph. And if you do that, then you have that they are actually more powerful because you have some algebras in the hypergraphs that are, for example, non-associative or something like that, like taking just some compositions. And that's like the main part of the research. There's also this one that I was talking with Cersis, because in representation theory, you want to study algebras from the representations of a graph that is more algebraic, like taking each vertex with a vector space and the arrows as linear transformations between vector spaces, like. And you can study some properties of finite dimensional algebras with those representations. So there is something that was created last year, that is the hyperquiver representations, that are like multilinear representations when you have a hypergraph. That's a nice paper that was from some people on Oxford, with someone in Harvard, that were discussing how to extend the notion of quiver representations to hyperquiver representations. So this was like a more further research. And yes, that's it.
Great. Okay, thanks so much for that. Yeah, if there's any questions from anyone in the audience, or if there's additional information anyone needs, please reach out to the Institute. We have a brand new website, so if you go to the community page on the website, you can join our Discord. Sergio will be there to take any further questions or comments. So with that, thank you so much for joining us. This was an excellent presentation, and we'll